Good morning. So today we're going to start going through net ionic equations and looking at those a little bit more closely. I brought them up at the very beginning of this unit. This would probably be the last topic in our unit on chemical reactions, but I'm trying to not even really think of things as units anymore because everything for the rest of the year pretty much builds off of the topics that we talk about that come before it. And we're also not taking any large assessments at the end of a unit. So what we're going to be dealing with next is really going to just build right off of net ionic equation. These net ionic equations are a topic that's going to be really, really important if you're going into AP chemistry next year. You see them all over the AP test. It's important to understand what's happening. It's important to be able to visualize them. So we're going to start to take a look at that today. And today we're really going to focus mostly on looking at these net ionic equations in terms of visualizing things. So we're going to go back and talk about particulate diagrams. Next class, we'll talk about how do I write a net ionic equation. So let me pull my notes up here. These are uploaded on Schoology, so you have them if you want to follow along with those. So I mentioned these at the very beginning of the unit and only in as much to say that we would come back to them later. A net ionic equation really think about a double replacement reaction. There's a lot of things going on in that reaction. And a net ionic equation really pares that down into what is happening in that chemical reaction and pulls all the extra species, the extra things out of there and lets us really focus on what's the chemical reaction that's happening. So a net ionic equation is a chemical equation for a reaction, and it only lists the species that are actually participating in the reaction, are participating in the chemical change going on. What I would like to do today is take this idea and revisit particulate diagrams. If you remember, we had an extra day thrown in way back when, and we took that time and we looked at particulate diagrams. These, again, are going to be something that you're going to see a lot on the AP exam next year. A particulate diagram is an attempt to help us visualize or focus on what's happening on from an atomic level. So in a particulate diagram, we used color-coded pieces, balls, symbols to represent atoms, molecules, or ions. And we can then kind of push them around and join them with other things and see what's happening in a chemical reaction or how things dissolve. They're going to help us visualize what's happening on an atomic level. Obviously, atoms are way too tiny. We can't see them. So this is going to help us think about, all right, these two atoms are bonded to each other. What's it look like when something dissolves? What does it look like when a new product is formed? We looked at a bunch of these prior. We're going to draw some today. So let's say we're just going to draw a couple different species here to remind ourselves of what these particulate diagrams look like. And then I'm going to show you a couple animations and some demonstrations that are going to also use them to help you really picture and see what's going on in a chemical reaction. So let's say I'm going to need 5 atoms here. I'm going to just pick 5 different colors. All right, let's say we've got orange pieces, and those can be, we'll let that represent copper. Let's pick a different color. Let's do green. And we'll let green represent nitrogen. We'll let red be oxygen. So if you see a red piece, you're going to assume that that is an oxygen atom. We'll let blue be hydrogen. And then let's see, I need a chlorine. So let's do purple. We haven't used purple yet. So we're going to draw some atoms, some ions, some molecules, some polyatomic ions, and they're all going to be made up of these 5 atoms. So if you see an orange ball, you can assume that that is representing an atom of copper. Green is nitrogen, red is oxygen, blue is hydrogen, purple is chlorine. So up top here you have our key. And then down here, we're going to use that key and we're going to use it to draw some particles. So first off, you can use particulate diagrams to represent just a single atom. So copper, right? Copper is a monatomic atom. It's not like an H2 or a Cl2. So when I have copper, I can draw just an atom of copper, right? It's going to look exactly the same as, make that smaller, as what it looks like in the key, because it's just an atom of copper. But we can also use these particles to draw things that are a little bit more complex. Hydrogen in its atomic form is diatomic, right? So if I were to draw hydrogen, it would be an H2 molecule. Now an H2 molecule is made up of 2 hydrogen atoms that are bonded to one another. So I would expect a particulate diagram of a hydrogen molecule to look like that. I have 2 hydrogen atoms. And we're going to show that they're bonded just because those 2 atoms are touching each other. Okay, that's showing that there is a bond there. You could use it to draw some slightly larger molecules. So what's something that we see all the time? We see water. Let's draw a molecule of water. Now, in a molecule of water, you need to start thinking about how things are bonded to one another. So in a water molecule, I'm going to have 1 oxygen that's bonded to 2 hydrogens. So I'm going to take my red oxygen and put that in the center. And then that is bonded to 2 blue hydrogen. So that would be a particulate representation of a water molecule. I tried to draw the structure a little bit. If you think back to water, it's a bent molecule when we did Lewis structures. So I showed that in there. Hydrogen is going to be smaller than oxygen, so I drew them a little bit smaller. These are things that you'll figure out and you'll see as you move along. But as long as you have the oxygen and the hydrogens there, you're really seeing what's going on, so you're in good shape. Let's see it, say maybe something similar. We can have a molecule of copper 2 chloride, CuCl2. Now, here's the thing. Copper 2 chloride is an aqueous solution. And I know that that doesn't follow specifically the solubility rules that we had talked about, but if you remember, I told you there's a lot of other things that come into play there. There's a lot of other rules. I gave you the minimum, the basic ones you need to be familiar with and memorize. Anything else, you'd have a chart, you'd be able to figure out that copper 2 chloride is an aqueous substance there. So when we draw this, we don't want to draw it as a discrete molecule. We don't want to draw it like our water molecule over here. Because when something's dissolved in water, remember, we don't have a copper 2 chloride molecule. What we have is a dissociated copper 2 molecule. So I'm going to have copper ions and chloride ions. They're not sticking together. Remember, each of them individually are surrounded by those water molecules. They're dissolved and they've broken up into copper ions and chloride ions. That's what it means to be aqueous. So when I draw my copper 2 chloride, I'm not going to draw it as one molecule. I'm going to draw it as dissociated ions. I've got copper And then I have 2 chlorines. Hold on. This glitched on me. Or I should say 2 chlorides because they're ions. So sometimes we want to label these as well. And another thing I want to bring to your attention is that this is not copper like this, okay? This over here is a copper ion. It has a charge. So this would be Cu with a charge of +2. And then each of these are chlorides, which have a charge of -1. So we'll label that to help make it a little bit more clear as well. So things that are aqueous, ionic substances in an aqueous form are going to dissociate into their ions. And we need to show that and represent that when we're drawing a particulate diagram. Copper oxide, CuO, is not an aqueous substance. That is a solid. That does not dissolve easily in water. So that we would draw as a molecule. A copper bonded to an oxygen. So a couple of different things here. We've got atoms. You can draw just something in its atomic form like Cu or H2. We can draw molecules, H2O, CuO, which would be a solid, so it stays bonded together. But when you see an ionic substance in its aqueous form, that means that it has dissociated into the ions that make it up. So let's try one more, something that is a little bit even harder or more challenging, but you're also going to see. Let's draw a particulate diagram for what copper 2 nitrate would look like. So CuNO3 2. So this kind of has a bunch of different things going on. And this, because remember, it has this nitrate, anything that has a nitrate anion is going to be aqueous, right? So what's my cation? My cation is copper. And when this dissociates, I'm only going to get 1 copper out of it because there's only 1 copper in the compound. So it's going to dissociate into a copper ion. Sorry, my notability gets glitchy sometimes when I'm mirroring it here. All right, so when this dissociates, I'm going to get a copper ion. Remember, this is an ion. It's a copper with a charge of +2. Okay. And then it's going to dissociate into 2 nitrate ions. So this NO3 is a polyatomic ion. If you remember, the bonds that hold together a polyatomic ion are covalent bonds. They're not going to break and form into nitrogens and oxygens floating all over the place. When this dissociates, we're going to get a copper ion and 2 nitrate ions. So each of those nitrate ions is going to be an NO3, an N bonded to 3 oxygens. And each of those nitrate ions is going to have a total charge of -1. So if I'm going to draw them, let me go back and check. I made nitrogen green. And then oxygen is red. I'm going to make that a little bit smaller just so we don't take up a ton of room here. So each of these is an NO3 and has a charge of -1. Okay, so just a little reminder of particulate diagrams. This is really to help us visualize what's going on in the chemical reaction. And then a net ionic equation, when we're writing those, is going to help us really focus on the important parts. So between these two things, the particulate diagrams and the net ionic equations, we should have a really solid understanding of what's happening on an atomic level in a chemical reaction. Again, we've got atoms. We can draw a molecule like water, H2O. We can draw ionic substances. So when they are aqueous, that means that they have dissociated into their representative ions. Copper ions and chloride ions in the case of copper 2 chloride, and copper ions and nitrate ions in the case of copper 2 nitrate. But when those ionic substances are insoluble, they're precipitates, they don't dissolve in water, we would draw them like a molecule, just like we would draw like a water. Okay? So what we're gonna do two things. I'm gonna show you an animation of some net ionic equations, and you're going to see a couple different things. It's about 2 minutes long, and you're going to see a chemical reaction for what's happening, and then you're going to see test tubes with the particulate diagrams, the little particles floating around. So you can see here's what the reactants would look like. Here's what the product looks like afterwards. I'm going to let you watch it through, and then I'm going to replay it a second time and pause it and just talk a little bit about what's going on. So I'll play it the first time here, and then I will play it back again for you. There's no sound, so it's not that you're not hearing something. All right, so I'm going to put that all the way back to the beginning. We're going to talk through a couple things. I'm going to pause it while this is going on so we can chat through things. All right, so in this first example, you've got water, which is a liquid. Water molecules are not ionic. They don't ionize. They're going to stay together as water molecules. And then you have aluminum chloride, which is a solid. So let's pause and look at what's happening here. You've got the aluminum chloride dissolving into the water. So this is showing how something's dissolving into the water. You can see here that the water molecules don't break apart, but the aluminum separates from the chloride. And each aluminum chloride compound or formula unit is going to separate out into one aluminum ion with a charge of +3 and 3 chloride ions with a charge of -1 each. Let's see if there's anything different really there. It's just showing how these things are dissolving. All right, let's take a look at this, and we'll look at the particles here in a minute. So we've got sodium chloride and potassium sulfate, both aqueous solutions. When the products are formed, sodium sulfate and potassium chloride, those are also both aqueous solutions. So you've got each sodium chloride separates out into a sodium ion and a chloride ion. And then we've got potassium sulfate, which is separating out into 2 potassiums and a sulfate. So into its representative parts that make it up. But what happens when you put them together, and I wish they would zoom in on this, is that nothing really happens because the products also are both aqueous. So in essence, all you have are a bunch of ions that are floating around in the solution. So this is going to show you how we write a net ionic equation, and take a look at it, but we'll focus on writing these next class period. This is showing you where these twos come from. So 2 sodiums, 2 chlorides, 2 potassiums, 1 sulfate. The 2 for the sodium and the chlorine come because there is a coefficient of 2 in front of there. The 2 potassiums come because within that formula, there is a subscript of 2, so there's 2 potassiums. But on the product side also, everything's aqueous. So I'm gonna pause that for a second. Does the reactant side look any different than the product side? If ionic compounds that are dissolved in water are going to dissociate into their representative ions, and everything's aqueous on both the reactant side and the product side, then nothing really happens. This is why in a double replacement reaction, the rules are you need something that is either a solid, a liquid, or a gas to say that a chemical reaction happened. Because otherwise, you've got all of these ions floating around. And when we write ionic equations, we cancel out what are called the spectator ions. And we'll define all this and practice it next time. But ions that appear both on the reactant side and product side aren't really doing anything. They're just floating around in the solution. So if we cross out everything that's the same on the reactant side and the product side in this reaction, nothing's happening. Now in this reaction, it's going to look different. So we've got magnesium chloride and potassium carbonate. You can see magnesium ionizing into magnesium and 2 chlorides, and then the potassium carbonate ionizes into 2 potassium ions and 1 carbonate. And when you put them together, whoop, look at that. So this magnesium ion found this carbonate, and magnesium carbonate is insoluble. It forms a precipitate. It doesn't stay dissolved into solution. So that's going to drop out of the solution and form a precipitate on the bottom of the beaker or test tube. And we do have some ions here that are left over floating in solution. We have the potassium that originally came from the potassium carbonate, and you have the chloride that originally came from the magnesium chloride. So these two we would consider to be spectator ions. They stay in solution the whole time. But we have this precipitate that's forming. And you can see that in the particulate diagram, it is drawn as something that's together now. And then they're going to go through writing the net ionic equation. Again, watch it, but we will practice this another time. The one thing I want you to realize here is, remember, each of these things that are aqueous split apart into their ions, but this magnesium carbonate is solid. So just like we wouldn't draw it separated out into ions, it also stays together in the ionic equation. Comes from that magnesium and that carbonate. Everything else, spectator ions. So this is a net ionic equation. This really helps you focus in on what is going on in the chemical reaction. All right, so one other thing that I want to share with you, and then hopefully a quick homework assignment to do related to this second thing. I'm going to show you a demonstration. So if I go back to my notes, this is on what you need to do is on the last page of the notes that I gave you. I'm going to show you a really quick demonstration of a double replacement reaction that happens between aqueous solutions of potassium iodide and lead 2 nitrate. We're going to watch it. You can make some observations about what happens. Actually, I'll just go ahead and play that for you now, and then we'll talk about what you should do with it. So the potassium iodide and the lead 2 nitrate are both aqueous solutions, and they're both colorless. So we're going to see what happens when the two are added together here. This is like 10 seconds long. There you have it. You have this pretty yellow precipitate that's forming, and it's all falling to the bottom because that precipitate is denser than the water is. Okay. You can rewind that and watch it again if you would like to. But here's what I want you to do with that. I'm going to ask you, and I don't have a specific place for you to do this, so wherever you would like is fine, to draw me a particulate diagram for what happened in that reaction. So just like the ones that we saw in the animation that I showed you, they had a test tube that showed us what reactant A looked like on a particulate level as a solution. And they had another test tube that showed us alone by itself what B would look like. And then they showed us what the product of the reaction would look like as well. So draw me a diagram like this, but obviously filled in with what things would be in each test tube, of what the potassium iodide looks like, what lead 2 nitrate solution looks like, and then what your product would look like on a particulate level. And you can go back, you can rewatch that animation to get an idea of what types of things you should draw. You can go back in the notes when we drew some of those examples together, but draw me what's happening there. I also, under that, want you to identify what that yellow solid is. Tell me what the yellow solid is based on your knowledge of solubility rules and double replacement reactions. Identify what that yellow precipitate is and write me a chemical reaction that shows the production of the solid. Now that can be a double replacement reaction, or if you want to take a stab at writing it as a net ionic equation, you can do that as well. But choose in some way, shape, or form, write me a chemical reaction for what happens. So particulate diagram, identify the yellow solid, and write me a chemical reaction. I will post an assignment on Schoology for you to turn those in. The first thing that we're going to do next class is look at some of them and go over it. Go over any questions we have about particulate diagrams, and then we will dive into how do I go about actually writing these net ionic equations from the balanced chemical equation. So touch base with me if you have any questions. Otherwise, I will see you all on Wednesday. Thanks. Have a good day.